All right, welcome to the lesson on implicit differentiation, where we ask ourselves, what do we do when it's difficult or maybe even impossible to write y explicitly in terms of x, and yet still need to find the derivative of y with respect to x? So, for example, let's say we have a graph of a circle with radius 5. I should still be able to figure out what's the slope when x is 2 or when x is 5. We should still be able to calculate the slopes of those tangent lines, even though this is not a function. And if you remember, we would express this as x squared plus y squared equals the radius squared, which in my particular example I'm saying is a radius of 5, so equal to 25. So how are we going to find the derivative of y with respect to x when we can't actually solve for y? Or, we could solve for y in this one, but we would have to square root an expression, which would give us a plus or minus root, which is like a whole piecewise thing. It's really messy. So this would be the one where it would be considered difficult, but not impossible. So let's take a look. So let's find the equation of the tangent line to the circle x squared plus y squared equals 25 at the point 3, 4. Okay, so our steps here are similar to previous derivatives and tangent line problems. The first thing we have to do is find that slope, that instantaneous slope, which means we have to find dy dx. Okay, so I'm going to rewrite the original equation. And again, we're finding the derivative of y, the function y, with respect to x. Okay, so whenever we're looking at these variables, the y is considered a function. X is just a regular variable, but y is a function, so that's going to be important here in a second. So if we were to find the derivative of x squared, that would simply become 2x, and the derivative of y squared, that's going to be a lot like having a function squared. Okay, so I have a function squared. If I find the derivative of that, we're going to use the chain rule, right? So it would be 2 times the function times the derivative of that function, except we're just using a y in this particular example instead of function notation. So the way we're actually going to write this is 2 times y, right? That would be like this step here where our exponent comes down front, the function stays the same, times the derivative of the function. And we notate that in this particular case as dy dx instead of using the function notation. Equals, and then the derivative of 25, that's a constant, simply becomes 0. And you might want to make a note, since this is kind of the part that makes implicit differentiation different. We're using the chain rule here. Since y is a function. Okay, so that's kind of the new part. The rest of it should feel pretty familiar. Okay, so again, we're trying to solve for the derivative of y with respect to x, so we need to get this term by itself. So the first thing we need to undo is this plus 2x. So I'm going to have 2y times the derivative of y with respect to x equals a negative 2x. Just subtracted that over. The next thing I need to do is undo this times 2y, so I'm simply going to divide on both sides by 2y. And so I get negative 2x divided by 2y, which we can simplify to just negative x over y. And so this is how we will find that instantaneous rate of change for any given point on the circle. Okay, so now we're going to put it all together and actually write the equation of the tangent line. Okay, and for that we need a point and a slope. If you remember, they gave us the point. Right here it's 3, 4. So now we just need to find the slope, which we just realized from above. We can plug into our equation of the derivative. Okay, so if we're working with the point 3, 4, that's what they gave us. That's an x and a y. We simply can plug it in. Okay, so here's our derivative formula. If we actually evaluate that, we're going to get a slope of -3/4. Okay, so now we can put it all together. So y minus 4 equals -3/4 times x minus 3. And that's all there is to it. Okay, our next example, we'll take it up a notch. So x cubed plus y cubed equals xy squared. So this would be one that we would not be able to solve for y no matter what we did. It's not just that it would be difficult, it would be impossible. So we have to use implicit differentiation here. So we take the derivative of both sides, so x cubed becomes 3x squared. And then here, don't forget, we're going to use the chain rule because this is a function being raised to the third power. So we're going to bring down the 3, keep the function the same, that becomes a power of 2, times the derivative of what's inside, which is the y. So that's dy over dx equals, okay, and then on this side we're actually going to have to use the product rule, right? So here we go. So first d last, and d last is again going to be the chain rule, so 2 times the function now raised to the first power, but I'm not going to write that, times the derivative of the inside, plus last, d first. Okay, and remember, x is not a function, so when we derive him, he simply becomes 1, whereas that's not the case for y. Alright, so let's try to clean up this right side. I like to pull all my variables out front. ABC order is ideal, but not really required. Okay, so that gives me that. So you'll notice we have dy over dx on both sides. So we're going to have to do a little bit more algebra here. We need to get both of these terms on the same side so that we can factor out a dy over dx. So I'm going to leave 3y squared times dy over dx over here, and I'm going to subtract this term over. Okay, on the right that leaves me with y squared, and I'm going to have to subtract over 3x squared. Okay, so we're just getting our terms together that have our dy over dx so that we can factor it out front. So GCF here, they both have this term. So dy over dx times, that leaves 3y squared minus 2xy in parentheses. Okay, so we just have one step left. Right now it's currently getting multiplied by this, so we need to divide on both sides by this parentheses to get our final answer. So dy over dx equals, it's going to be so beautiful, y squared minus 3x squared over that whole parentheses, 3y squared minus 2xy. And that is our beautiful answer to example 2. Alright, time for our last example. Differentiate sine of xy equals 2x plus 5. So again, something inside a trig function is super gross to try and solve, so implicit differentiation will allow us to do this much faster. Alright, get ready, because we have a product rule inside of a chain rule. Woo! Alright, so let's figure this out. So chain rule, let's do the derivative of the outside first. So the derivative of sine is cosine of what's inside unchanged times the derivative of the inside. So that's the product rule. So first, d last plus last d first equals, now the derivative of this side is nice and easy, that's just going to be a 2. Alright, let's try and clean some of this up. So let's see, that's just cosine of xy times this guy, dy over dx plus y equals 2. Now since we're multiplying this parentheses times this term, and I just need what's inside the parentheses, your fastest thing would be to go ahead and divide by cosine xy on both sides. Like, just move that term over there. Don't bother distributing it out when we're just going to have to kind of undo that anyways. So I'm going to divide on both sides by cosine xy, which leaves me with x times dy dx plus y on the left. And now I get 2 over cosine of xy on the right. Now, before I move anything else, this can actually be written not as a fraction, which is usually ideal for most of us. So if you remember, this is kind of like 2 times 1 over cosine of xy, right? And 1 over cosine is just, oh yes, secant. So we're going to rewrite this as 2 secant xy so that we don't have that fraction hanging out. What's scarier, fraction or trig? I don't know. I don't know. Alright, so now we're simply going to subtract a y. And of course divide by x. And really, that's all there is to it. It's just a lot of algebra and a good understanding of the chain rule. But other than that, it's really not as hard as it looks really hard. It's really not that bad. And that'll conclude our examples for implicit differentiation.